All right, folks. So you asked for it. A little bit of number theory. I dug up one of my old college textbooks, and I thought a good place to start would be with the division algorithm, um, which is really just like long division over and over and over again. But there are some pretty interesting things that you can do with it. So I'll let you just kind of play around with the first couple problems. But I wanted to show you how the division algorithm actually helps us with proving things. And that's kind of where you start getting going into number theory. So I'm looking at numbers 6 and 7 here. And so just so you know, the division algorithm is just the idea that if you've got two integers, a and b, if those are integers, and if b is a positive integer, then there exist unique numbers. So you can do this uniquely, and usually they use the letters Q and R, which are also integers, such that A is equal to BQ plus R, and R is in between 0 and B. And the inequalities are very specific. R could equal 0 if they're evenly divisible, but R has to strictly be less than B. Otherwise, you could take away another B from the A value. So anyway, that's the division algorithm. So let's look at it in the context of number 6. So use the division algorithm to prove that every odd integer is either of the form 4k plus 1 or of the form 4k plus 3 for some integer k. Okay, so let's look at an odd integer. So let's just say let z be an integer. Could have used any letter. I just wanted to use z. So let z be an integer. Um, Actually, I messed up already. Well, not really messed up, but let's actually talk to say z is an odd integer. So let z be odd. So then z equals 2n plus 1 for some n. That's an integer. That's what it means to be odd. So every odd integer is either of the form 4k plus 1 or 4k plus 3. And so what we're going to do then is look at dividing z by 4. And so what we know is that z is equal to 4 times q plus r. And what we can do is say that r is strictly in between 0 and 4. So the possible values of r are 0, 1, 2, or 3. And we can even write in that the n equals 1, the 2n plus 1 on the z value there. So what we know then is that 2n plus 1 is equal to 4q plus r. And what we can do here is um, show that the only possibilities for r are 1 and 3. And then we've proved the, the result. So one way to do that is to just go through and just plug in each of the values. And so if I plug in r equals 0, I have this statement here. So maybe let's just kind of, I'll move my face out of the way. We'll do the different cases over here. So if I do, let's do purple for cases. If I do r equals 0, then I have 2n plus 1 equals 4q, and that is a contradiction because this is odd and this is even. If I do r equals 1, then I have 2n plus 1 equals 4q plus 1, and this is okay. This is possible because this is odd equals odd. If I have r equals 2, hopefully you can see where this is going. 2n plus 2 equals, 2n plus 1 equals 4q plus 2. And this is, again, I can write this as 2 times 2q plus 1 if you want to be really specific about why this one here is odd and this one here is even. And same idea for r equals 3. So this one's a contradiction. So r cannot equal 0, r cannot equal 2. And then for r equals 3, we have 2n plus 1 equals 4q plus 3, which is equal to 2 times 2q plus 1 plus an extra 1. And so we have odd equals odd. And we're good. So that's one way to do it. There might be a more elegant way to do it rather than running through the 4 different cases. But the key idea here is that the division algorithm restricts the different remainders to be 0, 1, 2, or 3. And the only ones that are odd are the plus 1 and the plus 3. Let's look at question 7 as well. So prove that the square of any integer a is either of the form 3k or the form 3k plus 1 for some integer k. And so the hint here is given to us that we should be thinking about dividing by 3. And so we're looking at dividing 3. So if I have a is an integer, then it must be true that a equals 3q plus r, and r is in between 0 and 3. So we have 3 different cases. 3q plus 0, 3q plus 1, or 3q plus 2. And so then there's really only 3 options for a squared. And let's write them out. This one is 9q squared, which is 3 times 3q squared. In other words, it's 3k. This one over here is 9q squared plus 6q plus 1. And maybe what I'll do is I'll just give myself a tiny bit more space for the last one. So 9q squared plus 6q plus 1 is equal to 3 times 3q squared plus 2q plus 1, which equals 3k plus 1. And the third one of a squared would be 3q plus 2 squared. This is probably the most interesting one. This is where we get 9q squared plus 12q plus 4, which you can factor a 3 out in a little bit of a strange way. Plus 1 there, because 3 times 1 gets me 3, plus 1 extra, and then that becomes 3k plus 1. And so what we just proved is that for all integers a squared equals 3k, or a squared equals 3k plus 1 for some k in the integers, which I guess that's interesting. And the integers here, you can even go one step further, that k has to be greater than or equal to 0 because you squared the a value. So there you go. Very similar process on question 8. Prove that for every odd integer a squared is of the form 8k plus 1 for some integer k. So I'll let you think about that one, and please comment, ask questions, and enjoy your first forays into number theory.